traversing along a bank turn of circular radius r. So as the diagram shows here, if this is the bank turn, pretty bad circle, that would be the radius r. So now let's say you do not want your car to slide off the bank turn, because that would be quite unfortunate. Calculate the velocity without friction, then the maximum velocity and the minimum velocity, assuming that parts B and C involve friction. Okay, so this is like a very classic mechanics problem that involves circular motion. So if you think you can solve it, go ahead and pause it. And when you're ready, come back to see how I solve it. Okay, so I'm assuming you had a go at it. So let me start off with the case where there is no friction and the velocity must go for it to not slip off. Part A. I'm going to draw a short little snapshot in time of the inclined plane that it's basically shown. This is the angle theta that the bank turn makes. So over here, if I can draw a small little visual representation, that would be the inclined plane as such there because it's banked. This is the car here. I'll just denote that as like a small circle. There's only two forces acting on it. There's a force acting downwards, which is the gravitational force Fg. There's also the normal force, which is normal to the plane, acting this way, which I'll call Fn. Okay, since there's no friction, we don't have to worry about that here. So let us resolve not Fg, but Fn instead. Why? Well, you'll see why after we resolve Fn into its components. So acting upwards like such and acting horizontally. The vertical component will be, well, this right here would be theta, and this right here would be the same as this angle, this component here. This component here is adjacent, therefore it is Fn cos theta, and over here is opposite, so it'll be Fn sine theta, which is same over here, F sine theta. Now it has been resolved into its components. There is one acting in the upwards direction and one acting horizontally. The force acting horizontally, Fn sine theta, acts something like a centripetal force to the car. As such over here, if the car is reversing as such and there is a force pulling it towards the center, that's centripetal force. And the force pulling it towards the center is the horizontal force here, which is Fn sine theta. So we can set that equal to the centripetal force, which is, mv squared over r. Okay, so what about in the vertical direction? Well, Fn cos theta acts upwards, Fg acts downwards. So I can say that Fn cos theta minus mg is equal to ma. But since there is no net movement in the y direction, there is not going to be any acceleration. So I can set this equal to 0. Or in other words, I can set Fn cos theta equal to mg. Okay, now what I'm going to do because I have Fn over here, up here, and Fn up down here, I will simply divide by cos theta. So divide by cos theta on both sides. And also let me cancel out the cos theta here. So I'll be getting that Fn is equal to mg over cos theta, which I can now substitute back up here. So I get Fn, which is mg over cos theta times sine theta is equal to mv squared over r. M and m cancel out. I'll get that sine theta over cos theta is tan theta. So g tan theta is equal to v squared over r. Take r to the other side. V squared is equal to rg tan theta. Or finally, v will equal to rg tan theta all under the root. And that's the velocity without friction. Okay, let us look at the case where we want to find out the maximum velocity we can go when there is friction. B. Let's draw the same sort of diagram we had up here. So drawing it as such. Likewise, again, there is a force of gravity acting downwards, Fg, a reactive force acting upwards, Fn. Now we have to think about the motion of the car. If it's driving at its maximum velocity, it's going to be going slightly up the incline, right? So it will be maybe around here after it goes to maximum velocity. And since it's moving up the incline, the frictional force has to act in the opposite direction. So then frictional force will act downwards. Okay, now let's resolve Fn, and I'll call this F frictional, FFR. Let's resolve them into its components. So as such, again, we have Fn cos theta acting upwards, here's theta, Fn sine theta acting horizontally. Now let's resolve F frictional. Theta over here, this acting downwards will be FFR sine theta, and this acting horizontally will be FFR cos theta. Now note, we want this car to go without slipping off the bank turn. So therefore, the frictional force will actually be a static friction. It's the maximum velocity you can go without it sliding off, which is basically the definition of friction, static friction. So therefore, we can say that FFR is equal to mu S Fn. Now that's going to be useful for when we make our Newton's second law equations. Okay, so let's look at first our horizontal components here. Okay, so horizontally we have F and sine theta in the direction of the unit vector I hat. We also have FFR cos theta also in the direction of I hat, and that is equal to mv squared over r, just like last time. Now FFR is equal to mu s Fn, so I can say Fn sine theta plus mu s Fn cos theta is equal to mv squared over r. Let me factor out the Fn. Fn sine theta plus mu s cos theta is equal to mv squared over r. That is going to be our first Newton law equation. Now let's look at the forces in the j hat direction. So we have Fn cos theta acting upwards, F frictional sine theta acting downwards, and Fg also acting downwards. So we get that Fn cos theta minus F frictional sine theta minus Mg is equal to 0. Now again, firstly, I will move Mg to the other side. So this equals Mg. And let us substitute again F frictional for mu s Fn. So I'll get Fn cos theta minus mu s sine theta is equal to Mg, or Fn is equal to Mg over cos theta minus mu s sine theta. Now I can substitute this equation for Fn back up here, which has velocity. So we get that Mg over cos theta minus mu s sine theta times sine theta plus mu s cos theta. That is equal to mv squared over r. Let me first cancel out the m's and bring r to the other side. We get that, oh, I scrolled too far down. V squared is equal to rg sine theta plus mu s cos theta over cos theta minus mu s sine theta. And therefore, we'll get that velocity is equal to rg sine theta plus mu s cos theta over cos theta minus mu s sine theta, all under the root. Okay, and that is our answer for part B. This is the maximum velocity. I should probably specify it by writing V maximum. Okay, just one more just one more part left, which is finding the minimum velocity. So finding the maximum velocity, if you didn't find that too hard, then you probably find the minimum velocity to be a very similar process. Um, Otherwise, it's if you didn't get it, don't worry. Maybe you'll probably get the minimum one, and then that will help you. They're both very similar methods to get that. So one more time, draw the inclined plane, angle theta here. This is the ball here. Sorry, the car. I'm just modeling it as a ball. Downwards is force of gravity Fg, reactive force acting upwards Fn. Now, if it's going slower than its original speed, it's probably going to move down the inclined plane as such here. And thus, because it moves down the inclined plane, frictional force acts upwards, so up here. So let's draw it up here, F frictional. And now let's resolve once again into its components. So up here, I have F and this is theta here, so it's cos theta, F and sine theta. Now let's break this up into its components. F, Fr, if this is theta, then this is cos theta. And up here will be F frictional sine theta. Yep, sine theta. Okay, once again into it, this is the horizontal direction, this is the vertical direction. The force is in the horizontal direction. Okay, let's see here. We have Fn sine theta acting here, and backwards there's Fr cos theta. So we have to say Fn sine theta minus F frictional cos theta is equal to mv squared over r. Now remember here, FFR is equal to mu s Fn. So I can rewrite this by saying Fn sine theta minus mu s Fn cos theta is equal to mv squared over r. And now let's factor out the Fn, Fn sine theta minus mu s cos theta is equal to mv squared over r. Okay, let's find Fn by looking at the forces in the vertical direction. So acting upwards is Fn cos theta. Acting upwards again is F frictional sine theta, and acting downwards is Fg. So I'll get that Fn cos theta plus F frictional sine theta minus mg is equal to 0, or that this is all equal to mg. Am I right? Fn cos theta, FFR sine theta. Yep. Once again, this is the same thing as saying Fn cos theta plus mu s Fn sine theta is equal to mg. Factoring out the Fn, I get cos theta plus mu s sine theta is equal to mg, or Fn, normal force, is equal to mg over cos theta plus mu s sine theta. Now let's substitute this equation up here. I'll get that mg, so sine theta minus mu s cos theta over cos theta plus mu s sine theta is equal to mv squared over r. Cross out the two m's and rearrange to get r on the other side. Then by the same process, you'll get that v minimum is equal to rg sine theta minus mu s cos theta over cos theta plus mu s sine theta, all under the radical. So hopefully you understand now how you would solve these problems. I tried to make it as easy as possible, but it's quite a difficult concept to get your head around first time. It took me quite a while to understand it, but once I got it, it just clicked. You got to just remember the best way to do it is probably to resolve it to keep the unit vectors in basically the x-axis and y-axis as such over here, because that, for me personally, that was the easiest way to do it instead of making this way the inclined plane, making the inclined plane the unit vectors at an angle. It was easier just to have the unit vectors as two perpendicular lines, one acting vertical, one acting horizontal. So hope you enjoyed, and please stay tuned for the next video.